Without peers or pairs?
Or you will decide.
I know, I bring my own question.
Okay.
Oh,
So it's constructive. Constructive field theory without tears, yes. Ah. Okay, so it's a work with Vincent Rivasso, and I will try to cover the following things. So I first make an introduction, okay. Then I introduced the FIFO model as a gas of loops. Then from this gas of loops, I extract a tree for each term, extracting trees. Okay, then I have to go to show that this expansion in terms of trees converges. So convergence of the sum of trees. And this is in fact the main argument. And finally, if I have time, I will cover also let's say the decay of the two-point function. Okay. So let me just start. So our aim really is to simplify the construction of field theory models. So what we mean by that? So you remember you have the partition function. So lambda is a big volume cutoff. Then you have a covariance, then the coupling constant, and then the partition function is the integral over E minus lambda sum. So lambda, this is the coupling constant. Then big lambda is the volume cutoff of phi 4 of x dx. And d mu is a Gaussian measure, or the Gaussian measure, of covariance. So essentially 1 over minus Laplacian, okay? So that I write, let's say, in a 1 over p square in Fourier transform.
And that's C.
That's
C. 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 C is this.
C, yes, C. Okay, so the first thing in this kind of business is to show that okay, so you can define the pressure then. So this is the limit as the lambda tends to infinity of 1 over lambda times the log of z. Okay, and here for what concerns the 1 over p square, in general we put cutoff so as to have, let's say, in some sense only a finite number of degree of degree of freedom. That is, of the number of integration variables. And this is shown generally just by putting, let's say, in some more or less soft way, that the p. So here you put p squared plus 1 in order to have no infrared problem, and then you say p, smaller than something. Okay, and then constructing the model. In fact, means take the limit lambda to infinity and kappa to infinity. Okay, and in general, the way we know how to do that are, let's say, involved, complicated. So due to the fact that, huh? No, the kappa. Here.
There are two different P's on the blackboard, I think.
Yes.
Ah, P.
No, there is a P for the pressure.
The pressure. Oh, excuse me, this is pressure.
So P is the Fourier
Okay,
transform.
okay.
of
Yeah,
X.
but I mean, when kappa goes to infinity, nothing happens. Right?
No, it's enlarging the number of degrees
Of freedom.
That's true.
Okay, okay.
So it makes the Gaussian integral more complicated.
Yes, okay, if you want, the number of degree of freedom is something like this. It's lambda times kappa to the dimension.
Truly, C sub kappa, your family of covariances which have these ultraviolet cutoffs kappa, so they're smooth when kappa is small, but as kappa goes to infinity, these covariances C of x comma y get more and more singular when x and y are near each other. And the problem is to control that limit.
Okay? Okay, so here I look at just a part of the problem, okay, which in general in all this construction is, let's say, the building block. And so it's look at this problem here and to keep this one in the fridge. That is, okay, you look at P, let's say, okay, between m to the I and m to the I over 2. Okay, so you do that by taking the covariance to be, for example, okay, integral over m to the minus 2j plus 1 up to minus 2j of e minus alpha p squared plus 1 d alpha. Okay? And this more or less is saying that this.
Do you really mean m to the I?
mi over
I
2,
minus one.
excuse me.
Oh.
Or mi plus 1 here, I guess. I put it as it exists. Okay. Okay. So the result are that first the pressure exists. So this P here exists, and in fact it's something like this. It's and it's bounded by so the lambda, the coupling constant, times m4j. Okay, and in the same way, the 2-point function, so the 2-point function is f of s, x and y, and then it's the limit as lambda tends to infinity of the integral of phi of x, phi of y. Then this e minus lambda, big lambda, phi 4 z dz. Then the du, and then this being normalized by the partition function.
Are we in 4 dimensions?
Huh?
Are we in 4 dimensions?
Yes, we are in 4 dimensions. So, but we are in a slice.
I'm sorry, so the spatial dimension is 4?
Yes.
So this 4 in the bound on the pressure is really
Yes,
only if we're
exactly.
in
This
dimension
has
D.
to do with that, excuse me. Okay, and then we'll prove that this C of x and y, essentially, if you take lambda small, the coupling constant small, behaves more or less like the C which is here. Okay, and the C which is here, so it's something like this. It's, let's say, but it's more, it's also the behavior. So it's a m2j, e minus, and here you have an exponential decrease, which is like this. Okay, so that is a decrease, but with a factor which is here. Okay, which is, let's say, you see the dual of this. That it says more or less that x minus y is of order of m minus j. Okay. So. So how can you prove that? Then if you have this expression of the z, or let's say of the pressure, let's say the pressure, then you can say, okay, you have heard the whole week about Maya expansion and so on. So you would say, okay, here C is the thing which links different points. Okay, you have C, this is a C of Z and Z prime. On the other hand, the phi 4 term, phi 4 of X, it's just local, okay? So you would say, okay, I just take my favorite thing to extract a tree, and I just say, okay, the pressure is just the sum over the rooted trees in some point, so a starting point X, and then here you generate a tree of C's. Okay, and you have at the end, okay, what makes a phi 4. Okay, so that is non-integrated fields here. Okay, and here perhaps you have an extra field, and here an extra field to have at each vertex a phi 4. Okay, and then you integrate this with mu of phi. Okay, and here you have the sum of a tree. Okay, and this formula is just exact. The problem is it convergent? Okay, this is formally exact, but then how can you prove that this sum here converges?
Why is it trees rather than all connected graphs?
The same thing. Connected graph. I mean, if you make it something point-like, it's the same thing. So these are points. So that is here you have integration over all the points here. Okay?
I suppose what he wants you to put is that the measure here depends on the tree.
The measure depends on the tree, yes. But that depends on your favorite algorithm to extract trees.
Your favorite for
So you do that with Penrose, you do that with Brzezinski formula. I mean,
Okay, use one of those formulas to
yes,
write
one
the
of
sum
this
over trees.
recipe.
keep the rest of the
Right. And then if you were then doing the integral over phi, you'll connect up those extra leaves and
Yes.
create Feynman graphs.
Yes, yes.
Actually, you cannot use the Penrose formula because the d mu t wouldn't be a Gaussian measure.
Okay. Okay.
You have to use one of these forest group
Yes.
formulas for
Yes.
Okay.
interpolation.
So and here if you have
conversion.
okay, if you have the number of vertices is lambda is n vertices. So then here you have the lambda to the n. Okay? So I mean, if you are looking at a fermionic problem that is with Grassmann variables, this makes perfectly sense. Okay? So it just works. So it says that for Grassmann variables, the pressure is just analytic in lambda. And this because here the number of fields which are remaining here are the order 2n. There are 2n such fields. And so the Grassmann, the integral over Grassmann variables, even if there are 2n, just costs, let's say, or the weight is just a constant to the n. So a constant to the n with this lambda to the n, this just converges. So if you are, I see I'm here with bosonic things, then this doesn't converges. And that's just because if you have 2n fields and you are integrating them, this gives you an n factorial. Then you have lambda to the n factorial. Okay, just diverges. Okay. On the other hand, you have here that each lambda is in fact a minus lambda to the n. Okay, just because I had a minus lambda here. Okay, so this here is an alternating series. Okay, so you can say, okay, it's not analytic, but perhaps there are room for resummation. Okay, and what I'm talking about is how you can resum. Okay, so I now go to the next thing. So my second part is the phi 4 model as a gas of loops. The eraser.
There are many times here that
Thank you. Il y en a beaucoup. So our way of doing that for the moment is the following. So the phi-4 model, I can draw the phi-4 interaction like this. Okay, with here, so phi-4 of x. You have a point x here, and you have 4 fields. Okay, so one of our favorite trick in field theory is to split this in 2 parts. Okay, so we say, okay, we put an intermediate field. Okay, and it just looks like this. Here you have x, here you have y. And you say, here, okay, it's a propagator. And the propagator is a delta function. Okay, so you integrate over dy, and it's the same thing. Okay, so now, okay, you say, okay, it's a propagator, so, okay, it's the propagator of a certain field. Okay, so the propagator then, okay, I call this field sigma. Okay, there was minus lambda. So I choose to say, okay, it's I here square root of lambda. Here it's I square root of lambda. And so my new half vertex, if you want, is I square root of lambda of phi square sigma. Okay, I square root of lambda phi square sigma at point x. Okay, so another way of saying that is to say, okay, so I'm trying to put the numbers correctly. So you take E minus lambda. So this is the big lambda phi-4 of x dx. And you say just that this is, so the integration over this intermediate field d mu sigma. So this is, so once more, the Gaussian measure, but with covariance delta. Delta z minus z prime. So this is the covariance, the kernel, the covariance between z and z prime of E to the I square root of lambda phi square sigma z dz. Okay, so okay, it's just an explicit computation. Okay, it's a Gaussian. Everything is Gaussian, so or quadratic, and
You
okay.
forgot square root of lambda.
Square root of lambda. Excuse me. Okay. So once you have done that, okay, you can go back over there, and you say that the thing you are looking at is d nu of phi, d nu of sigma, and then e to the minus I square root of lambda phi square sigma of z dz. Okay, and then this time you are to integrate first with the d nu phi. Okay, so you interchange the thing, and you say that this is d nu of sigma, and then what you obtain is the determinant here of 1 plus IH, okay, to the power minus 1/2. So there is a determinant to the power minus 1/2 because it's a bosonic integration. Okay, and the H is C1/2. Here you have the square root of lambda sigma and C1/2. So I mean by this that, okay, H here is the operator of kernel, so Z, let's say between x and y. And so here I mean C1/2 of x and z. This taken at point z, and then C1/2 of z and y dz. Okay? And you see that this operator, so this is a simple computation. And okay, this H is emission, obviously. I guess. Okay, so I of H is anti-emission. Okay, so let me then develop a little this.
Sigma is white noise.
Hmm?
sigma is white noise?
Yes, exactly.
That's a nonlinear function of white noise?
Yes, yes.
Yes.
So on a lattice, it would just be a product of Gaussian
Yes,
intervals on each
yes,
subset.
exactly. Okay, so this was the Z, okay? And naturally, I guess here I have forgotten the fact that I had this volume cutoff. So here you must put the characteristic function of the volume cutoff. Okay, so that this remains in the volume cutoff. Okay. So then the Z, I can write as well as saying it's the determinant. The determinant is E minus 1/2 of the trace log of this 1 plus IH. Okay? So,
Integrated over.
oh, d nu, excuse me. Okay, so this is E minus 1/2, so the sum over P of minus 1/2, okay, minus 1 to the power P minus 1 over P, and trace of IH to the P. Okay, so I've just rewritten the trace log.
Sure.
And I call that a loop. Okay, you see, because it's a loop. It's a, if you remember what is H, this is C1/2 is sigma C1/2. So if you make a drawing for this, it's this. So with P terms, here you have an I square root of lambda sigma. Here another one, and you have P of them, and between them you have a C. Okay? Because 2C1/2, they just combine to make a C. Okay? So this is a loop, and so this is the exponential of loops. Okay, so this is phi4 as a case of loops. Okay. Okay, so I go now to the next topic, which was extracting trees. Okay.
Is this sum convergent for?
Huh?
Is this sum convergent for small? No. It's for small lambda.
Yeah, wait for a minute.
That will come. I mean, that's the full problem. I just said at the beginning, okay, it's true for fermions. At least if you don't do resummation, it's definitely not true for boson. Okay?
Because one thing that you just go up before you go up one blackboard, push that. I mean, one thing that's nice is, isn't it right that 1 plus IH has all its eigenvalues on the line real part equals 1.
Yeah,
so determinant to the minus 1/2 of it is actually bounded by 1.
Exactly.
Yes, yes. So,
That's
okay.
essential.
Okay, that's
You are guessing
Can I just make
before.
one remark to lay Bill Steers? That's a perfectly well-defined random variable for each x and y, because the c to the 1/2 is a smooth function.
Oh yes, there is no problem
yes.
with the mathematical definition, but this will
Yes.
come later.
at least as long as you take the big lambda and you are in a given scale, there is no problem.
Does the white noise measure make sense?
Yeah, because
if you smooth it.
each square root of c is a c infinity function.
What?
Each square root of the covariance is
No, I'm not worried about the C. I'm worried about the D nu.
The du is that's white noise, which is a very well Gaussian process. And then what you're allowed to do with white noise is to there's one random variable for each white
Yes.
noise smeared against a smooth function. That's what you have
Yes.
there.
Okay. Okay, so the next topic then is extracting trees. Okay, but what do you have here? Is a gas of loops. Okay, so the exponential of a sum of loops. Okay, and the loops are connected between themselves. They are connected by the integration over d nu. Okay, that is 2 sigma can contract and make a delta function. Okay, so you have a gas of loops. So these are the vertices. Okay, and this can make links. Okay, so links being delta function. Okay, so you take once more your favorite algorithm to extract a tree. Okay, I mean this time. Okay, the one you want. So okay, so
And in fact, they must all be linked up. You have to pair all of the sigmas, right?
you
have to pair all the loops.
no you have to pair. You have to pair all the loops. I mean, it will be okay. So the tree is something like that. You have vertices, and you must have a tree of connection between the loops.
But when you do the integral over the sigmas, isn't the sigma a Gaussian integral? So you
Yes.
have to pair all of these. With
Yes, but I don't do
Oh, you
all
don't
the
do that,
integrals.
yes.
I just extract a tree.
Oh, I
Okay,
see.
and okay, so here there are many sigmas, and I just integrate over them here. Okay, but here this is the extraction of a tree.
But here again, the measure on nu, you should put the dependence on the.
Naturally, here you have a sum over trees, and if you follow, for example, the Bridges-Kennedy formula, here you have it depends on t.
And the parameter.
Okay, and as you have heard, for example, if you use this formula, here the covariance between 2 sigmas here. Okay, it's so here let's say at point z and here at point z prime, then it's a delta over z minus z prime times the smallest s that you meet when following the when going from z to z prime on the tree. Okay, this is the Bridges-Kennedy formula. Okay, times so then the inf of the s on the path on the tree going from z to z prime. Okay, so okay, I want to be a little more specific, so I will try really to write this formula. Okay, it's perhaps not so useful, but just to fix the. I mean, it brings no more information than this, but. So it's something like this. So 1 over lambda of log z. Then it's something like this. It's the 1 over lambda integral over a rooted tree in x, dx, and the sum of lambda, and a of x. So it is a sum of. So first you have the sum over the number of loops. So from 1 to infinity of 1 over n factorial. Then you have the sum over the trees. Okay, and okay, because it's a rooted tree, I will say that the link, the first link of the tree, so the root, if you want. Okay, so each link, because it's a delta function, its link, in fact, is a point. Okay, it's at a point. So I would say that in this tree, the z0, okay, is x. Okay, then you have a product over all the L elements of the tree, but these L are variable, are, let's say, points. Okay, of alors, sum of 0 to 1 dsL. Then, so then, okay, this SL, this link here. Okay, so it's a certain point ZL, and it's between, let's say, a loop VL and another loop D prime L. Okay, so you have then, so you extract a sigma from this loop. So you have, So this is, I write like this, delta VL. This means that acting only on VL of sigma of ZL, and delta over delta V prime L, delta sigma of ZL. Okay, and you are naturally to integrate over the D or the DZL, but not the first one. Okay, so there is a. Then you have the product over all from 1 to n of all the loops. Okay, so I write that VL. So this is ZL. And from 1 to L of all this, so I call that big V of VL. This is the loop. And so they will be from product from 0 to 1 of all the VI, if you want. Okay? And then you have a product over all, an integral over all the points. Okay? But the first one. Okay, so this is the formula. Okay. So up to this point, in fact, there is nothing new, okay? You could perfectly have done that before. And the only thing why it was not used is that we are all believing that such a formula was just hopeless for boson. Okay? So it was perfectly good for fermions, just useless for boson. Okay, so we have certainly to do some resummation. Okay, so I go now to the next step. So perhaps I keep that. So I've still how much time?
Well, I think you started at least 15 minutes late, so you have still 10 minutes at least.
10 minutes, okay. So the next step is the main one, in fact, and perhaps I will stop there, is convergence of the sum of the trees. And naturally here, there must be some resummation, okay, in business. Okay, so let's look first at the sum of trees. Okay, to sum over the trees, so if you look at Kelly's theorem, it says that the number of trees linking endpoints with a coordination number kv at each vertex. So the coordination number is the number of links at point V. Is n factorial to the product over the V of kv minus 1 factorial. Okay, so you see this n factorial cancel with this one. And then you have still this. But you see here, you must do all these derivatives on a given V, okay? And this is extracting, let's say, the different links of the vertex in the tree. But when you are doing that, let's say you have all the orders, okay? And the orders of kv link on a loop is exactly kv minus 1 factorial. So it just cancels with the combinatoric of this. Okay, so what remains is just okay, the sum over n, the sum over the kv, and then the sup over the trees, because I've taken into account the combinatorics. And then you have to bound a loop, a tree. Okay, so it's like this. Okay. Okay, so to start with, I will first bound a leaf. So a leaf is a loop which kv is equal to 1. Okay, so there is just one link. So let me enlarge what is a leaf. So a leaf is something like this. You have, so the link, And here, it's like this. You have, so you have a C1 half here, a C1 half here, and then in between, you have, let's say, okay, all this, but no more link, okay? So it's just a succession of C's and sigmas, okay? But a succession of C and sigmas, that's exactly what we have called 1 over 1 plus IH. Okay, so it has the form of, so let me this point Z, of C1 half of Z and U, if you want. Then 1 over 1 plus IH between U and V. V is this point. And then C1 half of V and Z. Okay? Integral du dv. Okay?
And 1 over 1 plus
Huh?
H. Oh, 1 over 1 plus H is the
Is all these
series of
things
all
here.
possible
Okay,
ones.
okay. But you see, this is exactly f, a certain function f, which is this one, 1 over plus IHJ. And so this is bounded by the product of the L2 norms of the f and j times the norm of the operator 1 plus IH. Okay? But this one, IH is anti-emission. So the bound of this is 1, for example. Okay? So you are just remain with this. That is the bound. So, okay. So the L2 norm, okay, C1 half. C1 half. So C1 half square. And this is just, in fact, C of, at the same point, C of x and x. Because C1 half is positive, C is positive, okay? And so this is, if you remember, just N2J. Okay, because I've put this, I've kept it somewhere, I'm not sure. But the C1, the C between x and y was essentially N2J E minus N2J x minus y squared. So if you look at that at the same point, just remains M2J. Okay? So a leaf, and there is a square root of lambda. Okay? So a leaf is just square root, or bounded by square root of lambda times M2J. Okay? So we must just go on.
In 5 minutes. 5 minutes.
5 minutes, okay. Okay. Okay, so if you do that for every leaf, okay, so the leaf are no more there, so what remains are things where you have, let's say, the leaf, but you can replace the leaf by square root of lambda and 2j, okay? Or at least you have here a local insertion which is bounded by this. Okay, so these are my previous leaves. And here you have perhaps, you have, okay, so now I look at a new leaf that is, you have the previous leaves, and what remains here is only one link. Okay, so I do recursively, so it's the leaf which remains when you have first bounded the real leaves. Okay, that's the second leaves if you want. So you have a number of square root of lambda and 2j. Okay, and in between, so here you have the 2c1 half, as before. And in between, what you have is 1 over, here you have a c1 half. And in between, you have 1 over 1 plus IH. Okay, so you do the same computation. It's a c1 half here. Then you have 1 over 1 plus IH. Then you have a c1 half. Then this insertion square root of lambda and 2j. Excuse me. Here it's a lambda, in fact. Okay, so I must just argue on this. It's because here you remember, it was like this, but here this was square root of lambda m2j. But in fact, here you have another square root of lambda. So it makes lambda. Okay, so lambda m2j, then c1 half, etc. So this norm is bounded by 1. And then I will argue here that this is bounded by lambda, or let's say constant lambda. Okay? So let me look at the operator given by C, or the kernel of which is C1 half, lambda m2j, C1 half. M2j. Okay, so C1 half as an operator is just 1 over P. But P was more or less m to the j. So this is m minus j. Okay, and you can look do something a little better, but you will find really this. So this here you have m minus j, m2j just cancels, remains lambda. Okay? So here the whole bunch of operator is just bounded by lambda at the power of the number of insertions. Okay, so you find that this is bounded just by square root of lambda m2j times lambda to the power of the number of insertions. Okay? So, okay, it's finished. So I want to make still, before stopping, a little comment. So the main argument here was using 1 over 1 plus IH in norms smaller than 1. Okay, and this is where the resummation lies. Okay, so I'd say you need a resummation, the resummation is there. Okay, so in the previous proof, so this is for insiders, the previous proof, the non-perturbative argument was using E minus phi 4 smaller than 1. Okay, or integral of this. Okay, and okay. Okay, you see, this argument is an argument which has nothing to do with connectedness. Nothing to do. Okay, so you start with something which is not connected, you use that, you end with something not connected. Okay? So, okay, this bound has nothing to do with connectedness, and so it was completely orthogonal to it. Okay? Here, the 1 plus IH is down on the tree. That is, you know already that the things are connected. Okay? So it preserves connectedness. Okay, so this time I'm finished.
Well, just if I can add one, I don't know if it's question or comment, because Jacques is at the origin of so many of these things in constructive theory. Perhaps he forget to tell you, if you don't know it, that previously this kind of theorem was used with the decomposition of space into cubes, and with so-called cluster plus Meyer expansion. And so it combines also these two steps in one, and there are no cubes any longer.
Yes, no cube and no Meyer level 3.
Yes, David.
Is the radius of convergence, it seems to depend on m, right?
No, it's uniform. No, here you see the bound on this operator just lambda. Nothing to do with NJ.
Okay, I missed that. I see, right.
Nothing to do with J. So
Sergio?
perhaps depend on M, yes, but not on J.
Sergio?
The condition on lambda to converge is somewhere lambda must be positive.
Okay,
Yes.
so here you see it's I.
Square root of lambda.
It's I. In fact, if you want really, it's I square root of lambda C1 half something. Okay, something Hermitian. Okay, so you need that the real part, or let's say, you need that in fact the argument of square root of lambda is smaller than pi over 2. So it means that you need that the argument of lambda is smaller than pi. And in fact, if you say that the argument of lambda is smaller than pi minus epsilon, then you will get here a constant depending on epsilon.
So you get directly analyticity in a calculation.
Yes,
Yeah,
yes.
you get Borel
But naturally, it's not analytic.
It's Borel summary.
But
Yes.
That was well known by the cluster and Meyer expansion argument. Yes.
Yeah, you had a similar kind of expansion with Jagmotzer for the self-avoiding walk or something.
Yes.
But that was a multi-scale thing, right?
Yes, and no, there were cubes in that thing.
Well, okay, but I mean, you also use this.
Yes. There was an intermediate field, yes, but it was bosonic, in fact. This problem is bosonic, but if you want what they call with zero component, that is no determinant.
Yeah.
But it was really bosonic, and we used cubes.
Okay, so this is better.
Well, this
Yes.
is the first one without cubes. Yes.
You wrote your covariance as an integral over slice of momentum space. So you have a whole bunch of, you have these CJs that you have to all add up.
Yes. So our
Slice.
okay. So our let's say okay. So the one slice model is really the building blocks. Okay, that is, if you are unable to do one slice, okay, you must better do some other things. So we write in general. Okay, the C, as Vincent said, is a sum over the Cj. Okay. So here, in fact, I was looking at the Cj, that is this momentum P more or less between Nj plus 1, let's say, and Nj. Okay? But then you have a whole bunch of Cj. So we make the following picture. Here, this is slice J. That means exactly what I've looked at here. Okay? Then you have a whole bunch of things. Here you have G minus 1, G minus 2, G plus 1, and so on. Okay? And all the propagators can only contract a phi j to a phi j here. Okay, and this being the Cj I was talking about. Okay, and then so the phi is then a sum of orthogonal variables phi j. But you see the phi 4 then is okay, phi 1 plus phi 2 plus etc. plus okay, phi j plus etc. at point x to the 4. So it means the thing which couples the one slice model are phi 4 things. So each phi 4 you see can have fields in different slices. Okay? So our slices are coupled. And then, okay, the next thing then is to couple the slices.
I see. So you didn't tell us the whole story. There are tiers afterwards.
I mean, I had. Okay, but I told, let's say, okay, 2/3 are what I wanted, and I'm out of time. So
Constructive field theory with fewer tiers than previously.
With fewer tiers.
But no tears.
for the moment.
Still other
Less
questions?
tiers. Let's say, perhaps better say with less tiers.
With less tiers. Still other questions? Okay. If not, let's